As we reviewed before, a dynamic programming problem can be divided to two different categories. The first one is deterministic dynamic programming, and the second one is probabilistic dynamic programming. In this section, we want to focus on the concept of deterministic dynamic programming, where the state at the next stage is completely determined by the state and policy decision at the current stage. The probabilistic case, that is the other one, where there is a probability distribution for what the next state will be. That we'll talk it about this item in the next part. So, as you see here, deterministic dynamic programming can be showed and described as this figure 11.3. So at stage n, as you see here, at the stage n, the process will be in same state Sn, making policy decision Xn, okay, this is the contribution of Xn, then moves to the stage n plus 1, okay, and at this state, the contribution thereafter, okay, will be f star n plus 1 Sn plus 1, okay. So the decision policy Xn also makes a contribution to the objective function, combining these two quantities in an appropriate way, provide that Fn, Sn, Xn, the contribution of stage n onward to the objective function, and based on the decision, based on the question of the example, optimizing with respect to Xn, then gives Fn start Sn equal to Fn of Sn and Xn star, okay? As you remember, it's exactly, we are talking about the same notations and about the same elements that we learned in our prototype example, the stagecoach problem. In the next slide, with providing some examples, we focus more on this concept and learn it better. To categorize a dynamic programming, there are different forms to separate them and classify them. The first one could be based on the objective function of these examples. For example, the objective might be to minimize the sum of contributions of the individual states, or maximize the sum or minimize the product of the terms, whatever. But as you remember, as we reviewed in characteristics, this one could be maximizing or minimizing. The other categorization is the nature of set of states for the respective stages. In particular, states Sn must be representable by a discrete variable or continuous variable or state of vector, or it can be categorized by the nature of the decision variables, that they are discrete or continuous. Whatever they are, the decision variables always are the same form, x1, x2 up to xn. We should make a decision for the different states of our problem. As you remember, in the very first part of this chapter, we talked about that dynamic programming doesn't have a fixed structure of the examples, and there is no structured form of formulation of these examples, but they also always follow a same general rule to be solved. To this end, I told you, we review some examples, okay, in this concept to be familiar with this item and different forms. The first example that is important for us and is very interesting is distributing medical teams to countries. Guys, when I'm saying distributing medical teams to countries, is the form of this example important for us, obviously. Our aim is how to determine how many of 5 available medical teams to allocate to each of 3 countries. In the next slide, we have detailed the explanation of the example that is deciding about how to allocate 5 medical teams to 3 countries to maximize teams' effectiveness performance measured in terms of increased life expectancy. So, in comparison with our stagecoach problem, this part we are talking about maximizing, okay, maximizing the effectiveness. What is the measurement? Increasing the life expectancy. You remember there our measurement was the cost of the different rides and totally the cost of routes, minimizing the cost of routes. Here is maximizing effectiveness performance. So in the next slide, we'll have the explanation of this example, and after that, I solve it in this video. So let's focus on this example thoroughly, what it says. The World Health Council is devoted to improving healthcare in the undeveloped countries of the world. It now has 5 medical teams available to allocate among 3 such countries to improve their medical care, health education, and training programs. Therefore, the Council needs to determine how many teams to allocate to each of these countries to maximize the total effectiveness of the 5 teams. The teams must be kept intact, so the number allocated to each country must be integer. The measure of performance being used in additional person year of life. The table of the next slide will show the estimates additional person year of life for each country for each possible allocation of medical teams. What is the question? Which allocation maximizes the measure of performance? So, let's interpret what this example says. There are 5 medical teams that the World Health Council wants to allocate them to 3 undeveloped countries. So when we are talking about undeveloped countries, we are talking about lack of some items. So this allocation for sure will increase the level of life expectancy and the quality of life in these 3 countries. So as maybe you think, there are many different forms of allocation to allocate these 3 groups to these 5 groups to these 3 countries. Okay, for example, allocating 1 to the first one, allocating 2 to the second one, allocating 2 to the third one, or allocating all of the 5 groups to the first one and nothing to the other ones, allocating 3 to the first one, 1 and 1 to the second and third one, and many other examples that you can find. But through dynamic programming, we are trying to find a combination that is a maximum, that give us a maximum form of life expectancy among these 3 groups. This is our goal. We want to maximize the performance of these 3 groups. So the next slide will give us these tables, in a table, these allocations in each of these countries. So as you see here, this table provides data for World Health Council problem that are in thousands of additional person years of life. What is the meaning of that? It means that if we allocate one medical team to the first country, the additional person year of life will be 45,000, or allocating 4 medical team to country 2 will result 110,000, or for example allocating 2 to the third country is 700,000. As you see here, in each country there are different possibilities of allocation. From what to what? From 0 to 5. We can allocate nothing to one country, or 1 or 2 or 3 or 4 or 5. But for sure, deciding about each of these allocation, okay, we should think what are the other allocations of the other ones. We know and we are sure that this total allocation is equal to 5. No, because totally we have 5 medical team, and we know that this allocation should be integer because they are teams. Okay, we can't have 0.5, 0.2. So we need to know what are the allocations of these 3 countries that maximizes the personal year of life. So as you see, and it's obvious, if this allocation in each of these countries increases from 0 to 1 to 2 to 3, as you see, the life expectancy will increase here as well, here as well. But we can't have, for example, allocation more than 5. So we need to find a combination of these elements to have 5 and give us the best result among 3 countries. Okay, so let's move to the next part to explain what happens to this example. This slide shows graphically what we had in the previous table. Okay, so these are different stages, no? Stage 1, stage 2, and stage 3. As you see here, guys, you should pay an attention to one important item. Although we work on the concept of dynamic programming in a recursive, in a backward process, okay, and when we are talking about future and present time, okay, although when we have future, but because it's a backward form, we start to solve it before our present. Okay, so don't make a mistake about these 2 ideas. And one other important item. Always when we are going to allocate something, for example here the medical teams, at the stage 1, obviously what we have available in our hand is 5 medical teams. But based on the decision that we make here, that is 0, 1, 2, 3, 4, or 5, in our second stage, one of these items could remain for us. Okay, so what we had here as available is the only form is 5, but here for sure what it remains for us, it could be something like this, because we don't know about how is the allocation. The same idea happens in the stage 3. Stage 3 here is the country tree. We are not aware from the happening for the country 2 and country 1. Okay, for this reason we should review all these combinations as you see here, and as we talked before. For example, for this big example, doing something trial and error will take a long time, so we need to use dynamic programming solution. And one more item, always this allocation should start from the country 1 and moves to 2 and 3, but the solution is vice versa, start from country 3 to 2 and to 1. In our explanation, in our solution, we'll see how this one works. So as always, like the previous example, the prototype example that we had, we need to formulate always our example. Like here, the formulation of the example is, what are the decision variables? We just learned before that the decision variables, we show them with xn, okay? So how many decision variables do we have here? 3. Why? Because we need to make a decision for country 1, for country 2, and for country 3. Sn is the number of medical teams still available for allocation to remaining countries. So guys, in total, we have 5 resources. We have 5 medical team that we want to allocate them to each of these companies, these countries. So, as you remember, and as I told you in the previous slides, always this allocation starts with the first element. Here is the first country. So, for sure, when we want to start allocation, we still have 5 available medical team in our hands. Okay, so but the decision may change based on the decisions that we take, that it could be 0, 1, 2, 3, 4, or 5, as we saw in the previous table. But in the second country, the number that we have still available to allocate for sure is the number that we allocated in the first country, that it was x1, 5 minus this x1. So it could be whatever. If it's 0, 1, 2, 3, 4, or 5 for the first country, it's 5 minus this number. And what remains for us for the third country, we still don't know about that. But we can formulate it, that is S2, what was available, and what we allocated to the second country. Okay, so please don't forget the allocation always starts from the very first element, very first country here to the last one, but the solution is vice versa, is backward. So please don't make a mistake about these elements. Then, if I want to state the measure of performance by pi of the xi, okay, it means that the performance of the decision variable xi, whatever decision variable that we select, what level of performance gives us. So we show it with pi of xi. As you see here, we want to maximize this total of performances, okay, because this is the goal of this game. And obviously, we know that the total of these decisions xi should be equal to 5. Why? Because we have totally 5 medical teams that can't exceed from these 5 teams. Let's continue the formulation in the next slide. So as you see here, guys, like the example of stagecoach problem, as you see here, this function fn, sn, and xn is the performance of the current level plus what comes from level n plus 1, what comes from future, the maximum of that. So for sure, all those fn, sn, and xn that are available, but one or some of them are maximum. So f star n is the maximum of this function fn, sn, and xn. Okay? And one important item, I can write fn, sn, and xn equal to pn, xn, that is the performance measurement of this stage, plus f star n plus 1, that is this star shows optimality, here is maximum, sn minus xn, what remains for us for that level. In our solution, we'll see that. So the state, as you see here, is moving from stage n. Okay, this is a deterministic dynamic programming with the contribution of xn to sn minus xn. What it remains for us with the decision that we made in the previous section. So this type of example is a famous example and known as resource allocation. We want to allocate a resource to other elements. Here, our resource is medical team. We want to allocate them to countries, and always we want to maximize this resource allocation, this total. Let's go to the next parts. So in this slide, we want to review what is the solution. As you may learned before, we always start with the last stage, okay? Last stage, that is our third country in this example. Then we move to the second country, and then we move to the first country. Like the table of the stagecoach problem, we form this table that we have. As you may learn in the previous parts, in this stage, okay, in the country 3, the allocation of 2 and 1 just has done. but we don't know about that. So there are different possibilities that may happen. That is, for example, this 0 means that with a combination 1 and 2 just received 5 medical teams and none of them remains for here. If 1 means 4 of them just allocated to other 2, this 2 means 3 of them before here. If it remains 3 means 2 of them just allocated the other 4 in 2 and 1. 4 means just 1 of them allocated to one of these groups, and 5 means none of the countries 1 and 2 are just received the medical team. So for sure, these elements are coming from the table table 11.1 for the third country. If you see them, they are for the same table. 0, 50, 70, 80, 100, and 130. So this formula is exactly like the formula Pnxn plus Pn plus, F star n plus 1 is 3 minus x3. So when it's n plus 1, it means 4. But like the stagecoach problem, here we don't have the fourth country. So when it's for 4, it's equal to 0. So in this formula, the only item that says what is F star 3 S3 is the measurement of that we have in our table. As I told you, in the table 11.1. Now let's move to the next country, that is country 2. Pay attention, guys. We are going to maximize the performance by these allocations. So in the second country as well, we have the same form. Okay, we don't know how we allocated in the first country, but in this country we have different types of allocations. Okay, different kinds of remaining, and we can make a decision how to allocate these items. Let's see what happens. It says this 0 means for the country 1 remains, for the country 2, if remains 2, the only possibility of allocation is 0. Okay, it doesn't have any meaning, but it means that when I enter to the second country after first country, it means that I just allocated all the 5 medical teams to the first country. So for sure, 0 for the second country based on the table 11 is 0, and F3 star 0 comes from here, that is 0. So 0 plus 0 is 0. For example, this element 50, what this 50 comes, it means that it's the time that remains for us after country 1, 1 medical team, and we have two, no, not we have, there are 2 possibilities to allocation. Or if it allocates to this country, it means 2, it means country 2. Or if we don't allocate this one to country 2, when we don't allocate this one to country 2, for sure this one that remains goes to the first one. So if we don't allocate nothing in the second country, based on the table 11, this P2x2 is 0. And if we allocate this one to the third country, is 50. This F3 star S2 minus SX2. So 50 plus 0 is 50. The same happens here. This 1 and 1 means we enter to the second country with one medical team and we allocate this one to the second country. So for sure, what remains for the third is 0, because when this one remains here and we use it, there is nothing for the next one. So if you check allocation of one medical team to the second country, you will find 20. So this part is 20 plus F3 star of 0, F3, okay? F3 star of 0 is 0. So between 50 and 20, which one is maximum? 50. From what allocation comes? From allocation 0, okay? Let's go, for example, to this 4. Why we have here, guys, like this? Why we have 4 elements here? I have, why we have 5 elements, or why we have 4 elements? Obvious, because we can allocate 0 or up to that maximum. When it remains 4 elements for me available, it means or allocation 0 or 1 or 2 or 3 or 4. So as an example, this 115, it means that it remains for me 4 elements. I allocate 2 of them to the second country. So for sure it remains 2 for me for the other country. That is the third one. If I check allocation 2 to second country, it's 45. If it remains 2 for the third country, is 70. So 70 plus 45 gives me 115. The maximum of this line is, for example, 125. That comes from allocation 3 medical teams. Now let's check one item here in this table as well and make a solution. This is the country, it's the very first moment that we want to do the allocation, okay? We want to do the allocation, and when we want to start the allocation, we have 5 groups prepared, so available. I have 5 available, and for example here, if I allocate 3 to this one country, to the third country, it remains 2 for the next one. So 3 to the first country is 90. 2 from the second is 70. So 70 plus 90 is 60. All these elements of P and Xn comes from the table 11.1. So guys, let's check the solution. The solution says at the level 1, this 170 comes from the x1. This x2 is not correct, is x1. This x1, okay, is 1 that we should, because this 170 comes from this one, okay, this one is as an allocation of 1 unit to this country. What remains for us is 4. 5 minus 1. What remains for us is 4 here. What 4 says? It says the maximum comes from allocation of 3. Okay, so I allocate 3 to this country. So first country, 1 team. The second country, 3 team. So 1 plus 3 remains 1. For sure, it comes from this part. Okay, it comes from this part. What remains for us? It's 1 plus 3, 4. So 5 minus 4 is 1. So as you see here, 1 says we should allocate 1 to the third country. So the optimal solution is 170,000 person a year, okay, with the allocation of the first country 1, the second country 3, and the third country 1. This graph shows what we finished in the previous slide. As you see here, the total was 170, the total of the performance, the best performance, the maximum performance. And by allocating one medical team to country 1, 3 medical teams to country 2, and 1 medical team to country 3. So as you see here, it's these are these items 1 to country 1 with this 45 plus 75 and allocating 3, that is 75 plus 45, it gives us 120, and assigning 1 remaining to third country with this performance increasing 50. So 50 plus 75 plus 45, it gives us the same amount of 170 that we found in the previous part. Guys, these kind of examples, it's are known as resource allocation examples that always we start from allocating the first stage and moving to the last one. And obviously what it's available will be reduced by the number of we allocated on the previous part, and this allocation in total in different stages should be equal to the total available resources. In this case, we allocated medical teams as our resources to number of activities. So in a general form, resource and activities. In this example, resources are medical teams and activities are our countries. And so there are some familiar concepts. Stage N, that is activity N, okay, whatever that we have. In this case we have 3 countries, okay, N is equal to 1, 2, 3. X1 is the amount of resource allocated to activity. From those available, the decision variable, the decision that we make, we show with xn. Again, in this example, we have x1, x2, and x3. And finally, state Sn is the amount of resource still available for allocation to remaining activities. Okay, so obviously we allocate from Sn amount of xn. So when we move from stage n to stage n plus 1, our Sn will be changed to Sn minus xn. Okay, so this item, this type of example is one of the most important and easiest one of dynamic programming. Let's review our next example and see how the formula of this one is. Our next example that we'll see in the next slide is example 3 of our class. That the structure of this example is similar to the one for the World Health Council because it too is a distribution of effort problem. Okay, it's a resource allocation. However, it's recursive relationship differs in that its objective is to minimize a product of terms for the respective stages. At the first glance, this example may appear not to be a deterministic dynamic programming problem because probabilities are involved. But it does indeed fit our definition because the state at the next stage is completely determined by the state and policy decision at the current stage. Now we'll see our example 3, what is about it. This example 3 is very similar like the previous example of the World Health Council. That is a type of distribution of effort problems or resource allocation that I told you. Let's review to understand this example well. One example says, a government space project is conducting research on a certain engineering problem that must be solved before people can fly safely to Mars. 3 research teams are currently trying 3 different approaches for solving these problems. So what are our activities? Our activities are 3 research teams, like our 3 countries that we had in the previous example. The estimate has been made that under present circumstance, the probability that the respective team, call them 1, 2, 3, like our country that we had before, country 1, 2, 3, these 3 teams will not succeed is 0.4, 0.6, and 0.8 respectively. These are the probabilities that they fail. Thus, the current probability that all 3 teams will fail is multiplication of these items. This is one difference. There we had summation, but this part we had multiplication. In the solution part and in the formulation, we'll see how to review this item. So at this moment and based on the current situation, this failure probability is 0.192. Because the objective is to minimize the probability of failure, okay? So the measurement here is the probability of failure, and for us, the less probability failure is more important, and we are interested in this case. So we want to minimize the probability failure. For this reason, we want to minimizing this one. Opposite in comparison with the World Health Council example. There, we wanted to maximize it. So, because the objective is to minimize the probability of failure, 2 more top scientists have been assigned to this project. Okay, so again, we have the option of assigning up to 2 scientists. It means that 0, 1, or 2 we can select for each of the stages. Let's continue this example in the next slide. This table 11.2 gives the estimated probability that the respective teams will fail when 0, 1, or 2 additional scientists are added to that team. Only integer numbers of scientists are considered because each new scientist will need to devote full attention to one team, okay? Like the previous one, we just assign this one, we just allocate this scientist to one team because fully is devoted to that team, okay? The problem is to determine how to allocate the two additional scientists to minimize the probability that all three teams will fail. As you remember, without these two scientists, the probability of failure of three teams were multiplication of three of them, 0.4, 0.6, and 0.8. That was 0.192. By this allocation, we want to have a total probability less than 0.192. As you see here, guys, it's exactly like the previous table of the World Health Council. As you see here, these are the probabilities of adding 0, 1, 2 scientists, new scientists to each of these teams, to team 1, team 2, and team 3. As you see, guys, for sure, by adding more scientists, the level of failure, the probability of failure will decrease. Like the other example, you remember, by adding the medical teams, the performance increased. Okay, here is decrease, is vice versa, because here is minimizing, and decreasing means improving the situation of the example. So let's review the formulation and solution of this example in the next slides. The formulation of this example is very similar to the example of World Health Council, okay? Because here we just want to minimize a combination of allocation of these scientists to the projects. There we had allocation of medical teams to countries, okay? Some resources to some activities. Both of them are the distribution of effort problems. In this case, in the case of this example 3, stages N, N1, 2, and 3 corresponds to research team N, and the state Sn is the number of new scientists available for allocation to the remaining teams. So the decision variables are xn when n is equal to 1, 2, 3. Three research teams are the number of additional scientists allocated to team n. Again, like the previous part, let pi of xi denote the probability of failure for team I if it is assigned xi additional scientist. Xi means or 0 or 1 or 2. As given by table 11.2, if we let this multiplication denotes multiplication, this sign, the government's objective is to choose x1, x2, and x3. So, as you remember, before we had the probability of failure of 3 projects where multiplication of these three items. So, the probability of failure of each of these denotes P1, X1, P2, X2, P3, X3, that multiplication of these elements should be minimum, okay? And for sure, we know here that the total of the decisions that we make are equal to 2 because we are talking about 2 different scientists. Let's continue in the next slide. So, like the previous example, as you see here, the function of this example is the multiplication of the probability of the failure of this stage n, multiplied by minimum of what comes from the stage n plus 1, okay? The multiplication of the previous stages. So if it's one stage, is one of them. Is 2 is multiplication of 2, okay? And this one exactly is like the other one. Pn xn multiplied by f star n plus 1 Sn minus x1. What is available minus what we select. So Fn star Sn is minimum of these elements, minimum of Pnxn multiplied by F star n plus 1 Sn minus xn. In the next slide, follow this example, please. Based on the formulation that we did in the previous slides, as you see here, this formula, okay, this formula of F3 star, sorry, S3 is exactly like this formula, but with this difference that this one is 1, okay? So, guys, it means that it's complete because it's multiplication. This one is 1. So, the only item that has role in this formula is like this one, but with this difference that obviously is P3 of X3. What are the elements? You can find these elements in the column, okay, of the third company in table 11.2. As you see here, it means when there is only available 0 or 1 or 2, it means that for for research team 1 and 2, we just allocated each of them. For example, if it's 0, it means that we allocated 2 of scientists to 1 and 2, and what remains for us is 0. So the probability is 0.8. If remains for us 1, what is the meaning of that? It means that in total, in 1 and 2, in one of them we assigned 1, and what it remains for us is 1. But based on the reason that I told you, this one is the last activity and there is no more, we need to assign this one to this activity. And as you see, the probability of 0.5, and with the same idea, this one is 0.3. All these elements are coming from the selecting 0, from selecting 1, and from selecting 2. With the same logic like the previous example, these two last tables as well can be analyzed. Again, in level N2, based on what happened in level 1, in research team 1, we have these possible availabilities of the scientists, or 0 or 1 or 2. For example, here, this 1, it means that it remains for us 1. It means that it's just assigned 1 scientist to a research team 1, and it remains for us. There are two possibilities, or assigning in this research team 2, or nothing, assign this one and assign that to research team 3. So as you see here, it's P2x2. It means that the zero of x2 is 0.6, and assigning from table 11.2, and assigning 1, okay, that remains for the third research team is 0.5. So 0.5 multiplied by 0.6, it gives us 0.3. The same happens here. For example, this 0.2. It means that if there is available 2 scientists, what is the interpretation? The interpretation is that there is no allocation in research team 1, and from these 2 here, for example, this option says 1 assigned to this one. Obviously, the other one goes to the third research team, as you see here. So we should watch in our table, we should look at the research team, that the table of 11.2, assigning 1 scientist to team 2 is 0.4, 0.4, this formula, multiply by fs star 1, okay, fs star 1, that is 0.5. So 0.5 multiplied by 0.4, it will give us 0.2. Let's review this one as well and finish this table. What is the meaning of that? We are available 2, and the one possibility is assigning these 2 to this part. What is the meaning? It means that the level 1, the research team 1, just allocated nothing, and we want to allocate 2 of them now, and nothing remains for the third one. So the 2 of the team 2 is 0.2, and nothing for the first nothing for the third research team is 0.8. So 0.8 multiplied by 0.2 will give us 0.16. Like the stagecoach problem here, always also we want to minimize. What are them? So it means that this line, what is the minimum? It's only 0.48. This line between 0.30 and 0.32, which one is minimum? 0.32. And among these 3 items, 0.16. So this 0.48 comes from selecting 0 scientist. This 0.30 as well comes from selecting 0, and this 0.16 comes from selecting 2 scientists. Okay, so we form this column as well. And the first table is the table that's like the previous example. It's when we want to start to assign. So we are sure we have availability of 2 scientists, but like the previous part, I can make a decision or assign 0 or assign 1 or assign 2. Okay, for example, let's check this part. Okay, it means that we want to assign 1 to the first company, 1 to the first research team, that is 0.2, and 1 from the other level. Okay, 1 from the other level that is coming from previous, that is F2 star. That's what we start here, what we calculated here. F2 star, that is 0.3. So 0.3 multiplied by 0.2, it gives us 0.06. Okay, and the other items can be calculated easily like this calculation. So among these elements, again, which one is minimum? It's 1. So is 0.060. So the minimum of the probabilities of failures after adding 2 scientists to this 3 research team now is 0.06. Before it was 0.192. For 0.132 has decreased, has improved the probability of failure of these 3 teams. So with what allocation? Allocating 1, 2, the level 1 to the research team 1. So one scientist to research team 1. So when I have this 1, this S2 is the total minus this allocation. So 2 minus 1. So I should follow this line. 1 says we should allocate nothing to the second research team. So 1 plus 0, 1. What remains for us? 1. Okay, so 1 here says we should allocate one scientist, the last scientist, to the research team 3. So the conclusion, the failure probability of these 3 research team is 0.060 with the optimal solution of x1 star equal to 1, sx2 star equal to 0, and x3 star equal to 1.